Hey everybody. Okay, so this is practice problem number 1 for homework number 10. And we're just now starting to get into radiation. So this is our first radiation practice problem, which is really exciting. Okay, so we're going to start by restating the problem. So we've got a surface. I'm going to draw it just as a circle. And we're going to say it's kind of in this horizontal plane. And then we've got another surface, which we'll say is a circle, in the vertical plane. So we can draw a line. We'll just draw this line from the center of our horizontal circle to the center of our vertical circle. And then we're going to draw these lines, which represent the vectors normal to the surface, so going perpendicular to the surface. And we can define angles theta 1 and theta 2, where theta 1 is 60 degrees and theta 2 is 30 degrees. All right. We also know the area of these circles. Area 1, 10 to the negative 4th meters squared. The area 2 is 5 times 10 to the negative 4th meters squared. Okay, finally, the last and most important bit of information is we know the emissive power, the total hemispherical emissive power. Okay, and that is 5 times 10 to the 4th watts per meter squared. Okay, remember the emissive power, or capital E, is all of the energy that is emitted over all wavelengths. That's what total means, all wavelengths. Over all directions, that's what hemispherical means, for this surface per unit actual area of the surface. So that's the emissive power. We like emissive power. It's similar to a heat flux, right? That's kind of something we're shooting to get to. But we're going to find it's not very useful for what we're trying to do, which let's talk about that. So what is it that we're actually trying to do? Well, there's two things. What we're trying to do is, I wrote this somewhere. Oh yeah, find the heat rate from 1 to 2. So how much energy is leaving surface 1 and hitting surface 2? So how much energy from 1 is hitting surface 2? And then we're asked to find what is the heat, the irradiation flux on surface 2. Okay, so our next step is always to draw our energy balance. The energy balance here might be a little hard to draw because we're going to end up working in intensities. But just to redraw, I'm actually going to draw first an energy balance around surface 1 and then around surface 2. Around surface 1 for part A and around surface 2 for part B. Okay, now all we have to do is list our approach. How are we going to do this problem? Okay, so we know the emissive power for surface 1, but that honestly doesn't help us that much because the emissive power is just telling us, here's our surface, it's telling us how much energy is leaving per unit area, but then that energy is going to spread out. Kind of spherically, it's going to go in all directions. So when we've got surface 2 over here, not all of the energy leaving surface 1 is going to hit surface 2. Almost all of it is going to miss and go a different direction. So sure, we know how much is leaving surface 1 per unit area, but we don't know how much is hitting surface 2. So we're going to have to figure out how to do that. Well, what we need is some value, something that is conserved across this distance. And that, of course, is intensity. So our approach is to find the intensity of surface 1. Okay, and once we have the intensity for surface 1, we can find the heat rate using the intensity equation. Finally, we can find the heat flux using our newly computed heat rate and the known area of surface 2. All right, so let's get right into it. That brings us to analysis. All right, so I don't want to spend too much time here, but I think it's important to understand why intensity is important here. Like I was drawing up here, the emissive power only represents the emission from our surface. So that's how much energy is emitted per unit area. But we need to know how much from 1 is going to hit 2. So when we compute the intensity of surface 1, that intensity is uniform in all directions for surface 1. Which means as the energy goes outwards, what remains constant is the intensity. At any point, the intensity remains the same. The intensity of surface 1 stays the same. It's almost like an intensity field, kind of this constant perpetrating through the hemisphere, so that once we hit surface 2, we know how much intensity is there, and from that we can find the heat rate. Okay, but first, we need to get the intensity. So we need the intensity. We were given emissive power. So how does emissive power relate to intensity? Well, we showed in class that it's actually just equal to pi times the total hemispherical times the total emissive intensity. So total hemispherical emissive power equals total intensity multiplied by pi. Okay, so that means the intensity is equal to the emissive power divided by pi. And we know the emissive power, it was given to us, 50,000 watts per meter squared. This area is written per unit actual area, so the actual area of our circle, no projected area or anything like that. And then we're dividing by pi, and pi actually has units here. It has units of steradians, because what we did to get this pi was we integrated our intensity over all directions, which has units of steradians. Okay, so when we do that, we get 15,915 watts per meter squared steradian. Watts per meter squared steradian would be the units of intensity if it's not spectral intensity, right? So we are not looking at wavelength anywhere in here. We're just assuming that we've already integrated over wavelength. And so these are the units we should expect for intensity. All right. So we have intensity, and that's great because a different, more fundamental definition for intensity is our heat rate divided by the projected area. So this is the projected area of our emitted surface, and that is projected in the direction theta 1. So this isn't just any old heat rate. This is the heat rate moving in the direction of theta 1. And that's kind of looking like what we want, right? Because we've got, let's go all the way back to our original drawing. We've got heat leaving here. And we don't want to know the full heat rate. We want to know all of the heat leaving in this direction, which is theta 1. But then we also need to know not just to theta 1, but to a certain amount around theta 1. So you see, we need to have this kind of cone represented, which would be the solid angle. So that solid angle tells us how much of the hemisphere around that direction, theta 1, are we trying to consider here? So this is another part of our intensity definition. It's the heat rate divided by the projected area of our surface in the direction theta 1 multiplied by the solid angle around that theta. So this isn't just any heat rate, it's the heat rate in a certain direction for a certain solid angle around that direction, or a certain portion of the hemisphere around that direction. Okay, so you see this is our real definition of intensity, and what's great is we can actually find these bottom terms, multiply it by the intensity we just found, and get Q. All right, so let's do that. We'll start with the solid, pushed a button. We'll start with the solid angle. Okay, so we want to find the solid angle. All right, let's draw our circle yet again, this time on a hemisphere. Okay, so here's our other circle. So we need to know the solid angle of this circle on the hemisphere around our emitting surface. Okay, so in order to do that, we actually need to look at the projected area, because you see, if you were standing right here and if you looked at this circle, I haven't drawn it very well, but you wouldn't really see a circle, right? You would see a circle but kind of tilted away from you. What you would see is the shape projected onto the hemisphere where you're looking. And so we're trying to find the solid angle that the projection of this circle onto the hemisphere would take up for the full hemisphere. That's what this omega 2,1 represents. It's the solid angle of surface 2 with respect to surface 1. So how much of the hemisphere around surface 1 does surface 2 take up? All right, so the solid angle, its definition is the area of the object divided by the distance r from our center of our hemisphere to the object on the hemisphere. Okay, so now remember, this is the area of the object on the hemisphere, so we need the projected area. So that would be A2 times cosine of theta 2, because you remember here was our surface and the normal to the surface, and then this was theta 2 right here. So we're projecting this circle along this direction to get kind of more of an oblong circle on the surface of the hemisphere. And we're going to divide that by the distance, which we'll call R2 squared, between the bottom emitting surface and the absorbing surface. All right, so we're going to do that, and we know all these terms, right? We know area 2, 0.0005 meters squared. We know that theta 2 is 30 degrees, and we know the distance between them is 0.5 meters squared. Okay, so there's that. Now we are ready to combine these ideas. We're going to go ahead and move these bottom terms up here and say that the Q from surface 1 in the theta 1 direction for a certain solid angle around the theta direction amounting to this omega from 2 to 1. So how much of the hemisphere does surface 2 take up with respect to surface 1? It's equal to intensity times area 1 cosine theta 1 times omega 2 to 1. All right. Well, let's just keep going with this. Actually, you know what? I'm going to scooch this over here because we're going to need a lot of room. So our heat rate in this specific direction is equal to our intensity, which we already found was 15,915 watts per meter squared steradian. And then we need area 1, which is 1 times 10 to the negative 4th meters squared. And we need the cosine of theta 1, which is 60 degrees. And we need our solid angle, which is 0.0005 meters squared. Cosine of 30 degrees divided by 0.5 squared meters squared. So you do all this and you get 1.378 times 10 to the negative 3rd watts, which seems really small. But let's go look at our situation again. So the distance here is 0.5 meters. So there's half a meter between these surfaces, and look how small they are. They're tiny. Here's a tiny surface, and here's a tiny surface. So you have a really small surface relatively far away from another really small surface. We should not expect a very large heat rate. But that's why we have part B, which is to find the irradiation on surface 2. So we've got this Q coming in from surface 1 to surface 2 onto surface 2. So the irradiation is a heat flux, and it's equal to the heat rate hitting our surface divided by the area of the surface. Sorry, that should be a Q. So our irradiation is simply the heat rate we just found divided by the total actual area of our surface. These heat fluxes we always write with respect to the real surface, not projected surface, because usually we don't know what direction this is coming from, so we couldn't even write a projected surface, projected area for it. So that's 1.378 times 10 to the negative 3rd watts. Divided by the area of 2, which is 5 times 10 to the negative 4th meters squared. And that gives us 2.76 watts per meter squared, which is a decent number. Because we have such small areas, the small heat rate, but then the small area kind of coincide to make this normal looking heat flux. Okay, well, that's it for this problem. And I guess discussion. I always forget discussion. But on this problem, what we will discuss is small heat rate, but normal heat flux. Okay, thanks for listening.